Hello and welcome to video 8 of Functional Justin. This is a video series I make every 2 weeks or so about topics in functional programming, mostly with Scala, and I'm looking at a lot of Scala 3 features, the updated version of the language which is coming out around now. So today I'm going to talk about monoids and semigroups. So last video we talked about monads and the very interesting relation between monads and category theory. So I'm not going to talk about category theory much this week, except to say that you'll probably recognize that a monoid is a category, almost more obviously than monads are. And if not, don't worry, it's really nothing to do with the practical use of monoids. But what we're going to do this time is talk about monoids and semigroups, which are really a way of abstracting the idea of joining things together. So we can join numbers together in different ways, we can join complex objects together in different ways, and we can join strings and lists together, and we can also join embedded objects, so objects that have objects within them that also combine in different ways. And this is what monoids and semigroups are really useful for. So we're gonna, as always, live code everything you need to do this from scratch, and we're also going to be introducing the idea of opaque types, which is a new feature of Scala 3 and is really useful when combined with monoids and semigroups, and it's really useful when combined with the idea of type classes in general. So hope you enjoy it. We're going to do some coding. This time it's going to be probably less than the 30 minutes that the last video took. So let's get started. So we're going to start by implementing semigroup. So semigroup is a type class, so we can use a trait to define the methods on it. So semigroup is going to specialize type A, and it has this function called combine that takes any A and combines it with any other type A. And we're going to leave that abstract because the user will, each instance of semigroup will have to define that combine method, and we'll also define the operator that looks like that. If you look in Scala Z and cats, you'll see that operator is quite often used for combining semigroups, and so we'll just define that in terms of combine so that the instance creator does not have to define it as well. So that's part of the story, and the next part is monoid, which is also a type class, and it also specializes a type A, and it's going to extend a semigroup because it's going to have the combine method, and it will also have a method called 0 that simply returns a value of type A. So that's what the type class looks like. Let's also make a companion object on monoid so that we can define the apply function, and that will give us a way to summon a monoid of a particular type if we need to. So that's going to be a monoid of type A, and we need to put an A there, and that's just going to be M. So that's the type classes, and that's how we implement semigroups and monoids. So let's define an example instance for integer. So to define an instance of a type class, we use the given keyword, and then we're going to give it a name. We're going to call it int monoid, and that's going to extend monoid of type int, and then we can go ahead and define the methods. So the 0 method will return 0, and we'll see why we chose 0 in a moment. The combine function is going to just implement addition. So what we'll have here is a way to add things together if they're integers, and we'll also have the 0 element, which is a way to combine something when you don't have something. Now that probably sounds abstract, but we'll see what I mean by that in a minute. So we're going to define the combine function. It takes a right value of type A, and then it's just equal to left plus right, L plus R. So this shouldn't be a type parameter, should just be an int. Alright, so that's everything we need to make an instance of type monoid int. So now we can go ahead and use that. So far this hasn't given us anything special, but we'll see that we can build on this later and make something more interesting. So there we just combining 3 integers, and if I run this, then you should see that I'll get the result 60. So let's talk about how I chose these operations. So monoids come from category theory, and I'm not going to talk about category theory much in this video, but we saw last week how you can derive monads from being a category. Now, monoid is also related to category theory, and you'll see that it has these 2 operations, identity and an associative combine operation. And what we're going to do is just prove that. And there are 2 laws that monoids must behave according to. So we've got the identity. We'll actually have a left and right identity. And what that means is that if I was to take any value that has a monoid, so we'll just take 10, and I'm going to combine that with the int monoid 0 value, then what you'll find is that is exactly the same as 10. So you can combine something with the 0 value and nothing changes. So the left and right identity is stated this way. So appending something with 0 does not change it. So if we print that, we should see that we just get 2 10s. And the other thing we've got to think about is associative combination. Associative combination, which means that when you combine 3 things, it doesn't matter what order you combine them in. So I can take this example. Now I can combine 10 and 20 first, or I can put the brackets in a different way. So I could combine 10 with the result of combining 20 and 30. So just like addition itself is associative, so is monadic combine. Sorry, IntelliJ is trying to help me with the braces here and not helping. So that looks right. So let's run that. So there we go. So the result is 60 both times, and you can see that there's no difference between moving things around associatively. So this is all very basic stuff just from high school algebra, but we're going to build on this. We're going to combine what we've done to make more and more interesting things. So the next thing we can do is talk about different instances, and so we've seen that addition of integers is a valid monoid. How about multiplication? So what we can do is implement a multiplication monoid for integers. So we'll call it int monoid mult, and it's going to be a monoid that extends integers again. And what we need to do is to find the 0 value. So now the 0 value is not 0, because when you multiply something by 0, it makes it 0. So it breaks the identity law. So multiplying something by 1 is obviously the identity. So you multiply any number by 1, you get the same number back. The next thing we want to do is implement the combine. So let's just copy that one. And obviously for multiply, we're just going to do multiply. And you can see that I've got a lot of red now, a lot of wiggly lines, and that's because you can't define an instance for the same type. So we already have instance of monoid for int. So if you look at the error message, you can see that, well, that's not showing the right error message. But the real problem is that we have ambiguous, oh there we go, that's the correct error message. We have ambiguous implicits, right? So we can't do that. So what we'll do for now is we'll hide this definition inside its own object. We'll call it multints. And then our code will compile because the rest of the code can't see it. I missed the with off there. That will fix that problem. There we go. Alright, so now we have sort of 2 programs that can't see each other. So we've got the original int monoid, and now we've got the multiplication int monoid. So the question is, how do you make multiple instances of a type class and then select the right one? Well, this is where opaque types come in. So an opaque type is sort of like a type alias, but as far as the compiler is concerned, it makes a instance of a different type without us having to do anything that we used to do with value classes. So we used to wrap types up just to get a different type. But now what we can do is we can make our own opaque type. So we define it like this: an opaque type called a multint. In other words, an int that multiplies, and it's really just an integer. So now what we're going to do is make a type class that works with multints, not regular ints, and that will fix our problem, because now there's no ambiguity. Okay, and we'd also like a companion object so that we can make instances of multints, just to make it easier for the user. So we're going to make an apply method that can take a integer and return in a multint, and you see it doesn't really have to do anything. Oops. It just returns the integer, but the compiler will know that it's a multint. Alright, so now what we can do is if we want to combine integers, we have to turn those integers into multints to combine them using multiplication. So we can go and import that object that we created. So in a real program, this would be in a different file. And remember that in Scala 3, importing givens is different to importing other things in the namespace. So we have to import all of the givens and all of the everything else using that syntax. Alright, so let's take a look at this in action. So let's say we want to combine some multiplication integers. So we can let's make a couple of instances of multiplication integers first. So there's 10. So we've made two instances of multints, and now we can combine them with the same operator as before. When we run that, you should see that we get the multiplication rather than the addition. So we got 200. So you can see that we're using opaque types here to make new types that are not different to the ones that they're alias to. We still got we can still treat this like a normal integer, but as far as the compiler is concerned, it's a different type, and we can use that property to select different type classes. Alright, so now let's look at things we can compose on top of Monoid. So one thing we can look at is, how about the idea of summing a list? Alright, so now let's look at things we can compose on top of Monoid. So one thing we can look at is, how about the idea of summing a list? So if we sum a list in functional programming, we would typically use fold left. So let's say we have a list of integers, and what we want to do is calculate the sum of those integers. So we can implement that as a fold left, and the 0 value would be 0. And then we're going to make an accumulator, and we're going to take each A from the list, and we're going to add that to the accumulator. So that's a typical way to do to sum a list in a functional style. So let's just check that out. We can make a list, and then we can print out the sum of the list. And you can see that it's 15, which is correct. So if you look at sum list, the interesting thing about sum list is it doesn't have to be quite as specific as it is. In particular, if we had a monoid instance for integer, then we could improve this quite a bit. So we could call it sum monoid, and then we'll replace the this 0 here, first what we need to do is summon a value of the monoid type. So let's say we have a monoid int. Now I can replace this 0 with the 0 value, and now I can replace this accumulator with the combine function. And so those two things together give us the ability to abstract the sum operation a bit more. And you might notice that we also don't need integer anymore. We can just say, well, how about we just have any a? We just have any a that has a monoid instance. Now we can rewrite it like that. And then we can replace the list of ints with an a, and the return value is a, and there we go. Now we're not really doing summing anymore. We're just doing the fold essentially. So we can rename this fold. So now what we've got is just a way to fold any monoid from a list of a to a single a using the combine function. So now we could rewrite some list. We could just write that as a fold, and we don't have to do anything special apart from that. There you go, that's still correct. Now another thing we can do is there's a thing called fold map, and fold map is for when you want to do something like we want to do, which is, let's say we wanted to fold a list, but we also want to turn these numbers into multints so that we can get the product of the list instead of the sum of the list. So what we'll do is we'll call this fold map, and as well as taking a list of type A, it's also going to take a function that turns A's into B's. And what we're going to do is say that A is just any value, whereas B is a monoid instance, or B has a monoid instance. And then the return value is going to be of type B. We need a monoid of type B there, and that should do it. And then the last step is, as we walk through the list, instead of getting A's and combining them, we need to call our function to turn that A into a B. Okay, so now with fold map, we can take an ordinary list of numbers and turn them into multints. So we pass in the list, and we also pass in a function to turn them into multints. In other words, multint apply. And then when we run that, we should get the product instead of the sum. And there you go. So if you look in Scala Z, if you look in cats, you'll see a lot of type classes around this idea of folding. And so this is the abstraction it's built on. Okay, final thing, we're going to look at how you could nest monoids. So let's do a kind of complicated one. Let's say we have a map of some value. So we have a map of keys to values. We want to be able to monoidally append the two maps together, and we'll see how that looks. So we'll call this section nested monoids, and specifically appending maps. Alright, so what we need is an instance of map monoid. We'll call it map monoid. And we're going to give it some type parameters. So we need the key of the map is going to have a type k, and then we have the value of the type, and that's going to be v. Sorry, the value of the map will be v. And what we'd like to do is show that when we append the maps together, we're going to append the values together of anything with the same key, right? So that means that if we want to append v's together, then we need a monoid instance of type v. And then we're going to define this instance of monoid for maps of type KV. And we can go ahead and implement the actual functions. So what's the zero value? Well, first of all, let's give ourselves a monoid to work with. So we'll just summon a monoid of type V that we're going to need. So we can use it. But the next step is, what does our zero function look like? Well, the zero function, if you add two maps together, what kind of map could you add to a map to not change the original map? Well, the answer is the empty map, because we're going to essentially take the union of the two maps. So you could add an empty map to any other map and it will leave it unchanged, which is what we're going for. So there we go, an empty map of type KV. That's the zero function. And the combine function is a little bit more interesting. So it's going to take, on the left, it's going to take a map of KV. And then we're going to make an extension method that implements the combine, that takes a write, and that takes a map as well of type KV. So what's the implementation going to look like? Well, what we want to do is take the keys of the left map and the right map, and we want to see if every key has a value in each map, and then combine them together. So let's do L keys will give us the keys of the first map. Then we're going to append that to the keys from the right, and then we can do a fold. And the zero value is going to be an empty map. And then what we want is, we're going to have an accumulator again. We're going to have each key coming in, and we'll call it K. So what we want to do is, ACK is our new map that we're building to return. And we're going to update that. And what we want to do is look in the left map to see if it has a value for that key. So get or else key. And if it doesn't, we want to return a zero value of that type. So we can use our monoid 0 VM. And so that gives us the left value, and then we want to combine that with the right value, which is going to look like this. Get or else, just like that before. We're going to use the same key, and we're going to use the same zero value. And that's it. So that's given us the ability to take two maps and pen them together. So let's see that in action. So we have a map. We're going to have a key of string, and we'll use multInt. So let's say 30. And then I'm going to have a map. This map is also going to have a B key with the value 20. What is the error? Oh, wrong arrow. There we go. So that's one map. So we're going to demonstrate appending two maps together. So let's make another one. And this one is not going to have the key A. It's just going to have a key B. And we'll have the number 3. And then we'll have we'll have a key called C. Let's put 90 in there. And finally, what we're going to do is append the two maps together. So M1, M2. And what that should print is the combination of the two maps. We're going to get a single map. We got an error here. What's that? Combine. Found a V, required a K. I missed a thing here. This should be K. Okay, let's run that. And there we go. You can see that the map is the result of merging the two things together and multiplying together all the shared values for the same key. So that gives you an idea what you can do with monoids. You can build up, you can start with simple structures, you can build up more complex ones, and then you can append them together. So monoids show up a lot in higher order structures. We've already seen foldable. They show up with applicative functors and traverse. So really very simple but very useful constructs. So that's the end of this video, and I'll see you next time. The next video will be about monoid transformers, and we're going to look at the writer monad. And the writer monad is actually something that uses monoids to good effect, which is why we did monoids first. So if you like this video, please hit the thumb up button and subscribe, and tell your friends and work colleagues to watch the videos, and thanks very much. Goodbye.